Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at graphing ellipses. By the end of this lesson, we should be able to graph an ellipse given an equation, and given a graph of an ellipse, derive the equation. So, recall from the previous lesson that we have two forms that ellipse equations can come in. They can come in the general form, which is given right here, or they can come in the standard form depending on whether we have a horizontal ellipse or whether we have a vertical ellipse. Notice that A is the length of the major axis, B is the length of the minor axis, and H comma K is the center of the ellipse. So to graph an ellipse, we need to identify the center, the direction and length of the major axis, and the direction and length of the minor axis. We will plot the center first, then plot 2 points A away from the center in both directions, and plot 2 points B away from the center in both minor directions. Let's see some examples. So here in our first example, we want to sketch the graph of the ellipse given by the equation x minus 3 squared over 4 plus y plus 2 squared over 16 equals 1. First thing that I notice about this is that we are working with a vertical ellipse. I know it's a vertical ellipse because the larger number, the larger denominator, is underneath the y variable, meaning that our ellipse is being scaled larger in the vertical direction. Okay, so let's find the center first. We can identify the center pretty easily from the equation. We can see that the center is going to be 3, negative 2. And let me get blue here. Okay, 3, negative 2. Again, just remember to change the signs in front of the negative 3 and the positive 2 into 3, negative 2. The A value, remember that A is always bigger than B. So 16 is going to be a squared. If I take the square root of 16, I get a, which is going to be 4. And then the b value is going to be the square root of the smaller denominator. Square root of 4 would give us 2. So here's the strategy. We want to plot the center first. So let's plot the point 3, negative 2 on our graph, which is right here. Now A represents the distance from the center to one of the vertices, and remember that the vertices are located on the major axis. So if I go 4 in the, and remember this is a vertical ellipse, so if I go 4 in each vertical direction from the center, that's going to give us the coordinates of the vertices. So 1, 2, 3, 4, up from the center, 1, 2, 3, 4, down from the center. Next, we want to look at B. Remember that B represents the distance from the center to the co-vertices on each side. So we want to go 2 in each of the minor directions. And again, since this is a vertical ellipse, the minor directions are left and right. So 2 to the right, 2 to the left. Now we want to use these points to sketch the graph of the ellipse. Sketch to the best of your ability. I'm going to be cheating a little bit with the auto shape recognizer that this program uses. And even then, I'm probably not going to do the best job, but we'll see. I don't like that. We'll try one more time. We'll say it's good enough right there. We can see it's a good enough sketch of the graph of the ellipse. We can see the center, 3, negative 2, right there. We can see the vertices using the A term and the B term, A being 4. This is a vertical ellipse again, so we know the major axis is vertical. So 4 away, 4 up from the center, 4 down from the center. And then using B to go on the minor axis, 2 right from the center, 2 left from the center. Looking at our next example, we want to sketch the graph of the ellipse given by the equation right here. Notice this is in general form. Since we've already previously learned how to go from general form to standard form of an ellipse, I went ahead and showed the work right here rather than taking the time to work it all out. If you need to, you can pause the video here and go ahead and write down those steps. But basically, converting from general to standard form, we get x plus 1 squared over 25 plus y minus 1 squared over 9 equals 1. So let's go ahead and identify the center, the A term, and the B term. So the center we can see very easily. It's going to be -1, +1 once we change the signs. We can see that the a term, again, a is always bigger than b, so a is going to be the square root of 25, since 25 is the larger denominator, which is 5. And b is going to be the square root of 9, since 9 is the smaller denominator, which is 3. Okay, so using the same strategy, let's start by plotting the center, -1, +1. We know that a represents the major axis. Now here, this is going to be a horizontal ellipse. And the way I know this is a horizontal ellipse is because the larger denominator is underneath x. So horizontal ellipse, meaning that we're going to go 5 away from the center each direction horizontally. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now for b, again, b is the distance from the center to the co-vertices. That's going to be on the minor axis. So we're going to go 3 up and down from the center. 1 point here and 1 point here. Okay? And then again, let's go ahead and sketch to the best of our abilities. Remember, this is a sketch, doesn't need to be 100% accurate. That one looks pretty bad, though, so let's try another one. Ooh, one more time. Don't like that one either. Good enough. Okay, and we can see we get the general idea. Now, one of the nice things is that it's actually pretty easy to check our answers using a graphing calculator. And the graphing calculator that I'm going to use is the Desmos graphing calculator. So what I did is I took both of these equations, and I plugged them into separate lines on the Desmos graphing calculator. And let me go ahead and show you that. So here's the first one, and comparing to our graph right here, we're looking for some key points. We can see 3, +2. We can see 3, -6. And if we jump back over there, 3, +2 right there, 3, -6. And we can also see the points 5, -2, and 1, -2. If we look over on our graph, same deal, 5, -2, 1, -2. So we can definitely see that the graph that we have sketched is correct. Same thing, let's go ahead and check Desmos with this general equation. So we plug that in Desmos. Again, to save some time, I've gone ahead and done that. But this is the ellipse that we're getting in Desmos. Looking at some key points here, we can see -1, +4. We can see -1, -2. We can see 4, 1 right there. And we can see -6, 1 right there. Going through and double checking, we see the same points. Here's 4, 1. Here's -6, 1. Here's -1, 4. And here's -1, -2. Okay. So we can see that our answers were accurate. Now let's kind of work in the opposite direction. We want to see, if we're given a graph of an ellipse, can we generate the equation? And the general strategy is going to be to identify the center, find the length of the major axis, or really find half the length of the major axis, which is A, and find the length of the minor axis, or half the length of the minor axis, which will give us B. Then plug those appropriate values into the standard form equation for an ellipse. So here in our first example, we want to write the standard form equation of the ellipse graph below. Again, let's find the center first. So center is pretty easy to find. You actually have a number of ways that you can find it. This one is easy enough to just look at it and know that the center is at -1, -2. So let's go ahead and put the center at -1, -2. And circle that. A guaranteed way that you can find the center is you can identify the major axis or the minor axis, count all the way across. So if we counted all the way across, we'd have 1, 2, 3, 4, 5, 6, 7, 8. Half of 8 is 4, and if you just go 4 from either end, 1, 2, 3, 4, that'll land you right in the center. Because remember that the center is half of the major axis, or you can find the center by looking at half of the minor axis, or the midway point on the minor axis or the major axis. So for that matter, we also know that this is going to be a horizontal ellipse. We're going to be using that information later. So we know the center is -1, -2. We can see that the A term, the distance from the center to a vertex on either side, is going to be 4. This is for the major axis. The b term, or the distance from the center to a co-vertex on either side, will be the b term here, which is 3. So a equals 4, b equals 3. I don't like that. Let's be consistent. There we go. So given that information, and since we know that this is a horizontal ellipse, well, the equation for a horizontal ellipse, the standard equation, is right here. So let's plug in our values. X minus h squared, that's going to be x plus 1 squared, as we change the value of the x coordinate at the center, divided by a squared. Well, a is 4, so a squared is 16, plus, we're going to get y plus 2 squared here, again, changing the value of the y coordinate of the center, divided by b squared would be 9, equals 1. Okay, so x plus 1 squared over 16 plus y plus 2 squared over 9 equals 1. And again, let's double check this in Desmos real quick. So let's take this, and just for convenience sake, I went ahead and plugged it in, and let's compare some key features from this ellipse. So we can see the points -1, 1, -1, -5. We can also see 3, -2, and we can also see 5, -2 as well. And if we jump over to our graph, we can see these same points right here. Okay, so we know that our equation is accurate. Next, we have a, this time it looks like we have a vertical ellipse. Also remember, again, A is always going to be bigger than B. So since we have a vertical ellipse, we know the major axis is running parallel to the y-axis. It's our vertical. The major axis is vertical. That means that the A term is going to be half the length of the vertical axis. Well, we can count here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half of 10 would be 5, so we have A equals 5. Alternatively, you can locate the center, which is pretty easy to find in this case. We can see the center is 3, -1. Let's go and write that in. And like previously, you can calculate the distance between the center to one of the vertices on the major axis, and again, you'll get 5. The b term, which is half the length of the minor axis, well, the minor axis is 2. Half of 2 is, of course, 1. So A equals 5, B equals 1. So since this is a vertical ellipse, the equation, the standard equation, is a little bit different. Now we have x minus h squared over b squared plus y minus k squared over a squared. Because remember, for vertical ellipses, the a term, the larger term, is underneath the y variable now. So plugging in our values, x minus h squared over b squared, that's going to be x minus 3 squared over 1 squared. Well, we know that 1 squared is just 1. Anything divided by 1 is itself, so I'm going to get rid of that. So this is just x minus 3 squared plus, well, y minus k squared, that's going to be y plus 1 squared, divided by a squared. A squared is going to be 25 equals 1. Okay, and again, let's double check this in Desmos. Always a good idea to double check our work. So that's what I have right here, and let's look for some key points on the ellipse. We can see 3, 4. We can see 3, -6. Jumping over here to our graph, we can see those points as well. Here's 3, 4. Here's 3, -6. We can also see 4, -1, and 2, -1. And if we jump over to Desmos, we can see those points as well. 4, -1, and 2, -1. So that graph and that equation do indeed match each other. All right, last thing we want to do is look at a couple examples where we're going to be given some information, not necessarily on a graph, and be able to write the standard form equation based off of that information alone. Note that there are probably, or there's definitely more than one way to go about this. You could sketch graphs to see the different distances from a graph if you want to. The way that I'm providing is just one way to approach the answer. Okay, so in our first question, or in the first problem here, we want to write the standard form equation of the ellipse with vertices 2, 3, and 2, -5, and co-vertices 0, -1, and 4, -1. A couple things that stand out to me real quick. Number one is that, remember, the vertices fall on the major axis. And if you think about the points 2, 3, and 2, -5, the x value is staying the same. So 2, then 3 up, 2, then 5 down, meaning that the major axis is running vertically. So this is a vertical ellipse. That's the first thing to keep in mind, and that's going to be helpful to us because it's going to allow us to write the equation. Okay. So the idea here, in order for us to write the equation of a vertical ellipse, we need to find the center, the A term, and the B term. So I've split up this problem into a few different phases: finding A, finding B, finding the center, and then finally, with that information, we can actually write the equation. Okay, so let's start with finding the A term. So remember, A is always bigger than B, so we're concerned with the vertices. And the A term is going to be half the distance of the major axis. Well, if we think about it here, if we have the vertices 2, 3, and 2, -5, if we can just find the distance of the major axis and just cut it in half, then we're good to go. So think about the points 2, 3, and 2, -5. The x values are going to stay the same, so we really just need to find the distance between the y values, the 3 and the -5. Well, that's +3 and down 5. This total distance would be 8. And now that we know that the total distance is 8, half of 8 would be 4. So the A term is going to equal 4. Now, there's also an algebraic way that we can calculate that. We can use the distance formula just to make sure 100% that we're correct. So let's do that real quick. Using the distance formula, we know that's x2 minus x1 squared plus y2 minus y1 squared. I went ahead and labeled the co-vertices, or sorry, not the co-vertices, but the vertices in this case, x1, y1, and x2, y2. Doing some quick math here. And let's plug in some numbers. x2 minus x1, that's going to be 2 minus 2. So this piece eliminates itself entirely. y2 minus y1 squared, that's going to be -5 minus 3, which is -5 minus 3 squared. That's going to be -8 squared, and -8 times itself is square root of 64, which again, square root of 64 is going to give us 8, just like we saw using a more visual approach. So this is the length of the major axis, 8. And again, A is half the length of the major axis, or the distance between the center and a vertex. So that means A is equal to 4. Okay, so we're going to need that. Now let's find the B term, and we're going to do a very similar process. Basically, we're going to do the same thing, but instead we're going to look at the co-vertices, because if we find the distance between the co-vertices, you can find the length of the entire minor axis. And remember that B is going to be half the length of the minor axis. So once again, just for example's sake here, I'm going to use the distance formula to calculate. So the distance formula, x2 minus x1 squared plus y2 minus y1 squared. And let's see here, x2 minus x1, that's going to be 4 minus 0. y2 minus y1, -1 minus -1. We know that part's going to completely eliminate itself because -1 minus -1, that's -1 plus 1, which is 0. So we're really just looking at 4 squared, which is 16, which gives us 4. So the length of the entire minor axis is 4, and the B term is going to be half of that, so the B term is 2. Okay, so we have the A term is 4, we have the B term is 2. Next, we need to find the center, and you have a couple options for the center here. Recall that in an ellipse, the center is going to be the midpoint of either the vertices or the midpoint of the co-vertices. So we can use the midpoint formula, and we can easily get the center. So I'm just going to choose, doesn't really matter. I'm going to choose the vertices here. So 2, 3, and 2, negative 5. Let's use the midpoint formula. So add the x's together. 2 plus 2, that gives us a 4, divided by 2. Add the y's together. 3 plus negative 5. That's going to give us negative 2. Cut that in half. And this gives us the coordinate 2, negative 1. Again, you would have gotten the same exact points if you would have used the co-vertices. And you can also just kind of common sense your way through it. You know, if your vertices are at 2, 3, and 2, negative 5, and you find the midway point between those, it's pretty clear that that's going to fall at 2, negative 1. Same thing if I look at 0, negative 1, and 4, negative 1. Look at the midpoint between those two. It's pretty clear it'll be 2, negative 1. So finally, now that we have all this information, we have the A term, we have our B term, and we have our center, we can now plug those into the standard equation for a vertical ellipse, and we will have x minus 2 squared divided by b squared, so 2 squared is 4, plus y minus k squared, so that'll be y plus 1 squared, divided by a squared, well, a is 4, 4 squared is 16, equals 1, and that's our answer. Once again, let's go ahead and double check this real quick. So jump over to Desmos. There it is, x minus 2 squared over 4 plus y plus 1 squared over 16 equals 1. And we can see that we're supposed to have vertices at 2, 3, and 2, negative 5. I'll double checking that real quick. Here's 2, 3. Here's 2, negative 5. We definitely have vertices there. And we were also supposed to have co-vertices at 0, negative 1, and 4, negative 1. Well, here's 0, negative 1. Here's 4, negative 1. We can see that we indeed do have co-vertices there. So this is this equation that we've generated is absolutely correct, and it meets the criteria. All right. In our last problem for these notes, we want to write the standard form equation of the ellipse with vertices at negative 6, 1, and 4, 1, and foci at negative 4, 1, and 2, 1. So here's the idea behind this. A couple things first. Let's go ahead and identify if this is a vertical ellipse or horizontal ellipse. Well, notice that we have the vertices. Remember, the vertices are the endpoints of the major axis. So if we look at negative 6, 1, which would be like something over here, and then positive 4, 1, which would be like something over there, we can see that this is going to be a horizontal ellipse because the major axis is running horizontally. So I went ahead and made note of that down here. This is a horizontal ellipse. That means when we get ready to write our equation, I already know which equation to use, okay? So let's talk about strategy here. We know the vertices, and we know that the vertices are going to get us the A term because the vertices are on the major axis. But the other piece of information we know is the foci, and the foci are going to help us find the C term. Now, the C term isn't really helpful in writing the equation, but what the C term can do is that together with the A term and the C term, you can calculate the B term, because one of the equations that we have is that C squared equals A squared minus B squared. So the strategy for this problem is to use the vertices to find the A term, use the center and the foci to find the C term, and then use the A term and the C term with this equation to find the B term. Then we'll have the A term, we'll have the center by default, we'll have the B term, and that'll be everything that we need to write the equation of the ellipse. So let's go ahead and do that. So, finding the A term. Well, again, just like in the previous problem, the A term is going to be half of the major axis, and we can find the major axis by finding the distance between the vertices. So let's just common sense our way through this one. We won't write out the full distance formula. We have negative 6 up 1. Let's say that's a point up here. And then we'd have like positive 4 up 1 as a point over here. So we can see that the y value is the same. So horizontally, we just need to find the distance from negative 6 to positive 4. So from negative 6 to positive 4, the distance in between is 10. So length of the major axis is 10. Units. And we know that the A term is half the length of the major axis. So thus, A equals 5. Okay, so very quick and easy to find the A term. Now let's work on finding the C term, because again, we're going to need the C term and the A term to find the B term. So for the C term, we have to find the distance from the center to the foci, but we don't know the center yet. So the center is, of course, going to be halfway between the vertices. Well, let's think about this here. Halfway between -6, 1 and +4, 1. Well, we know that we're going to have a y value of 1 because we're on that horizontal line, right? So we want to find what is the halfway point between -6 and +4. Well, halfway between -6 and +4 is going to be -1. So the center is at -1, +1. And now we can find the distance from the center to the foci. And we can use either of the two foci, either of the two focus points, -4, 1 and +2, 1. So we know the center is -1, 1. So we want to go from -1, 1 to either of the focal points. I'm going to choose the focus point to the right of -1, 1, which would be 2, 1. And again, let's just think about this here. The y value is staying the same, it's staying 1. So really we want to find the distance in the x values. So from a -1 to a +2, that's a distance of 3. So the C term is equal to 3. Now, if you really wanted to, you could do the distance formula. -1, 1 to 2, 1. Let that be your x1, y1, and x2, y2. And you could use the distance formula just like we did right here to guarantee that you get that value. But either way, the C term is going to be 3. So now that we know the A term and the C term, let's use that to find the B term so that we can finally write the equation of this ellipse. C squared equals A squared minus B squared. Well, C squared is 9. A squared is 25 minus B squared. Let's go and subtract 25 over from both sides. So minus 25 minus 25. This is going to give us -16 equals -b squared. We can, of course, divide both sides by -1. This will now give us 16 equals b squared, which means that b is going to equal 4 once you take the square root. Okay. Now we have everything we need, because again, to write the equation of an ellipse, whether it's horizontal or vertical, all we need is the center, which we know, the A term, the B term, and know what kind of ellipse it is. So we have all the information that we need. Here's our equation for a horizontal ellipse, where the larger term A is underneath the x variable. And this is going to give us, let's see, x minus h squared. That's going to be x plus 1 squared. Divided by a squared, well, that's going to be 25 since a is 5. Y minus k squared, that's going to be y minus 1 squared. Divided by b squared, well, b is 4, so b squared is 16, equals 1. All right, and once more, let's go ahead and graph this just to check some of the key features here. I went ahead and saved us the time as usual. Here's x plus 1 squared over 25 plus y minus 1 squared over 16 equals 1. And the key features that we're looking for, we want to see that we have vertices at -6, 1 and 4, 1, which we can see right here. There's -6, 1. Here's 4, 1. And that we have foci at -4, 1 and +2, 1. This one's a little harder to visualize, but if we look over here, if you look at -4, 1 and 2, 1, those are definitely the focus points. Okay. So again, not too difficult of a problem. Just make sure that you're identifying what you have to do, in this case standard form, and we know that this is a horizontal ellipse, and once you've identified which equation to use, you know to find the center, A term, and B term.